Let us understand the purpose of control phase. In the improve phase, we find out and implement solutions to all the root causes of a project Y. In the control phase, we take the steps to make sure the implemented solutions are long-lasting and sustained. Let us understand why we need control phase for a Lean Six Sigma project. For example, before improvement, the performance of a process was like this. After successful implementation, the performance of the process has risen like this. And if there are no controls put in place, the performance of the process tends to roll back like this. So, the control phase is as important as any other phase of the Lean Six Sigma project.
In the control phase of a Lean Six Sigma project, we do three broad categories of activities. First, we verify the results of post-improvement. Then we make the necessary corrections if required. And finally, we institutionalize the process. Let us now look at the first set of activities, verifying the results. The first thing we do in control phase is collect sizable data on post-improvement performance. Depending on the business context, we collect the post-improvement data after a week, or a fortnight, or a month. For example, our project Y is Improve On-Time Completion of Digital Marketing Projects. Let's say we started this project in the month of April and implemented the solutions by end of June. In this case, we may start collecting the post-improvement data of on-time completion of digital marketing projects from the month of July onwards. After collecting the data, we measure the post-improvement performance. Let's consider the same example of Project Y, Improve On-Time Completion of Digital Marketing Projects. Let's say the goal of this project is to improve the on-time completion to 90%. During the measure phase, that is before the improvement is done, the on-time completion was 60%. And here is the post-improvement data for the first month after the improve phase. The data consists of 20 projects and their on-time completion status. In order to use the Z calculator for discrete data, we need to count the number of defects, in other words, the number of delayed projects. According to the data, there are 3 projects that did not complete on time. So the number of defects is 3, and the total number of defect opportunities is 20. So during the control phase, the first month data of post-improvement shows 85% against the goal of 90% for on-time completion of projects. This is how we collect the post-improvement data, measure the performance, and verify the performance against the goal of the project.
If the data points are within the range of UCL and LCL, the process is said to be under control, and the variation is due to common causes. If the data points are outside the range of UCL and LCL, the process is said to be out of control, and the variation is due to special causes. If the process is out of control, corrective actions need to be taken. For a standard control chart, CL is the mean of the data, UCL is mean plus 3 sigma, LCL is mean minus 3 sigma. It is very important to understand the difference between control limits and the customer specification limits. Control limits are derived based on the process performance. Control limits are used to examine whether a process is under statistical control or not. Control limits are usually called voice of the process. Customer specification limits are given by the customer in order to set the expectations for the performance of a given process. By using Z calculations, we measure the performance of a given process against the given USL or LSL. Customer specification limits are usually called voice of the customer.
Usually, the pattern of data points on control charts indicates specific scenarios of special causes. Let us look at them. If a data point goes above the UCL, it is a special cause scenario. In other words, we need to look into the data to see what went wrong on that specific day. If a data point goes below LCL, it is also a special cause scenario. If a control chart has 7 consecutive data points above the control limit, it is a special cause scenario. If a control chart has 7 consecutive data points below the control limit, it is also a special cause scenario. If a control chart has 7 consecutive data points continuously in upward direction, it is a special cause scenario. If a control chart has 7 consecutive data points continuously in downward direction, it is also a special cause scenario. If the data points on a control chart forms a cyclic pattern, it is considered as a special cause scenario. If the data points on a control chart shows a trend pattern, it is also considered as a special cause scenario. If significantly few of the data points fall in the central zone of a control chart, it is considered as a special cause scenario. If almost all of the data points fall in the central zone of a control chart, it is also considered as a special cause scenario. Usually, this pattern leads to suspicion that the data may have been manipulated. There are various types of control charts available for continuous data and discrete data. We will now look at each type of chart.